The first place we're going to visit in our star graveyard are novas. And novas, the typical nova comes in a binary star pair. Is that a redundancy? A binary star pair? A binary star in which we have stars that are at slightly different places in their evolutionary track. We have a white dwarf and a star that is larger and hasn't reached the white dwarf stage yet. One of the best known examples of this are the stars Sirius A and B. So Sirius is the brightest star in the nighttime sky. We typically use that as a singular word, the star Sirius. But the star Sirius is actually two stars. The main star, the bright star, which is the one that we can see with the naked eye, and Sirius B, its white dwarf companion, which actually wasn't discovered until the mid-19th century. So this shows two pictures of it. The one on the left is the visible light spectrum, and those flares, by the way, aren't coming from the star itself. Those are just artifacts of whatever it is that took the picture, the image gathering tool. But Sirius A, you can see it's this large blob here. And the fact that it's a large blob, that's not indicative of its size. It is larger than B, but you can't just say, oh, here's this size splotch, here's this size splotch of Sirius B, so that must be the ratio of their sizes. But in visible light, clearly A is much more visible. But if we look in X-ray light, as seen by the Chandra Observatory, which looks at X-ray light, we can see that Sirius A is actually a lot dimmer. It's not producing as much high energy radiation as Sirius B. So if our eyes were sensitive to X-rays, we would have first seen Sirius B and then later seen Sirius A, although they're closer together in brightness in the X-rays than they are in the visible. I mentioned in a nova there's a white dwarf and a star that isn't as far along on the main sequence, or isn't as far along in its evolutionary track. It's off the main sequence probably and into the red giant or supergiant stage. But a white dwarf is something that's approximately the mass of the sun and about the volume of the Earth. One interesting aspect of white dwarfs is the more massive they are, the smaller they are, because white dwarfs are essentially electrons and protons all squished on each other, and that squishing is difficult to do the more massive it is because they have energy states that don't want to overlap. I apologize for anthropomorphizing the fact that they don't want to overlap, but the more massive the object, the greater those particles can condense together. So you notice this says a 1.3 mass white dwarf, solar masses, that's what that M sub sun means. 1.4 masses, that's the cutoff for white dwarfs. A white dwarf cannot be more massive than 1.4 solar masses. Anything more massive than that is going to become a neutron star. The electrons and the protons will then combine together to form neutrons. So here's the nova, white dwarf, the companion star, a red giant. They're really close together in astronomical terms. So the white dwarf star pulls matter from the companion star. And when enough matter is pulled onto the companion star that the mass of hydrogen, because the outer layer of a star is essentially all hydrogen, that mass of hydrogen gets hot enough to start to fuse together, that fusion together releases energy. When it releases energy, energy is equivalent to mass, so it's also releasing mass as well. That release of energy we can see as a flash of light. Here's an image of that, an example of that. But when that mass goes away, then the process starts again. So nova typically occur again and again. There's a periodicity to them because the amount of time it takes to gather the first critical mass of hydrogen that will fuse together is probably going to be about the same throughout its history, because the actual mass of the white dwarf itself in this scenario is hardly affected at all. It's really just this shell of loose hydrogen that was pulled off of the companion star that is becoming the nova. Sometimes, though, enough mass is pulled on because there is a buildup. I mentioned that it's recurring, and most of the mass and energy gets pushed away, but not all of it. So there is a buildup of mass. And if there's a buildup of mass such that the white dwarf becomes greater than 1.4 solar masses, then it will start to fuse heavier and heavier, fuse elements into heavier and heavier objects. It doesn't just do the temporary hydrogen fusion and then release the energy. It'll actually build a shell and basically become the core of a star without that outer layer. And as this core then builds up, it can actually go supernova. So some of these binary star pairs just are recurring nova. Some of them continue that way. Some of them there's enough mass built up to go supernova. Here's an example of a supernova remnant that we can see today, the Crab Nebula. This star went supernova about 1,000 years ago. So there are really two main types of supernova. What I just described there, which was the binary star, so a white dwarf that gathers enough mass from a companion and goes supernova. And then there's the traditional supernova, a single star that the material at the core fuses together to form more massive material until it gets to iron, and then it goes supernova. The same with the white dwarf binary star supernova. Also, the turnaround point is when the endpoint is iron. Iron, when it fuses together, doesn't release energy. That actually requires energy. So that very quickly eliminates the outward radiation pressure. So there's just this inward pull of gravity. With the white dwarf supernova, that doesn't have the outer layer, so there's not quite as much mass infalling there. So you might say, well, how do we know the difference? How do we know there's a difference to begin with? Well, we can look at the luminosity pattern. So here's the luminosity pattern of a massive star supernova. So this would be what's going to happen with Betelgeuse or Antares, and then a white dwarf supernova. So the actual makeup of this, not a big deal, although it is interesting to point out that typical white dwarf supernova actually gets more luminous, but it drops off more quickly. The important thing is that these graphs have different shapes. So by looking at these different shapes, you can determine what type of supernova it is. The typical result of a supernova is a neutron star, and many neutron stars are observed as pulsars. So first off, what do we observe with a pulsar? So a pulsar, we would see that this neutron star, for the most part, is dark, but every so often, a very short period, in this case 0.033 seconds, this is the Crab Nebula pulsar, 0.033 seconds, it's bright, and then it's dim for most of the time, then it's bright, then it's dim for most of the time. Some pulsars have a secondary effect here as well, and the Crab Nebula pulsar does, but the main pulsing has this periodicity. So how does that come to be? Pulsars have super strong magnetic fields, and when the axis of the magnetic field does not correspond with the axis of rotation, and by the way, that's the same thing with our Earth. Our Earth's axis of rotation goes through the South Pole, where the penguins live, up through the North Pole, where Santa lives. The magnetic field poles are off from that. The magnetic field pole in the northern hemisphere is in northern Canada. It's not near where Santa lives. And in the southern hemisphere, it's not near the South Pole. So the Earth's magnetic poles are offset from the rotational pole. So if the Earth's magnetic field was strong enough, it would have this pulsar effect too. But as this neutron star spins around, so the spinning is its natural orbital rotation, and by the way, it's unbelievably fast. So a neutron star is many times the mass of the sun, but look at how quickly it's rotating, 0.033 seconds. We see this beam, so this beam here, either the northern part or the southern part, it's facing the Earth, and then it goes away from the Earth, and it faces the Earth again, goes away from the Earth, faces the Earth again. So this is happening for the Crab Nebula pulsar, 0.033 seconds. So think about that. That's something that's many times the mass of the sun is rotating in just this tiny fraction of a second. Our sun takes about 25 days to do a full rotation. This is doing it in just a tiny fraction of a second. And it's analogous to a lighthouse, so this is just kind of showing those two together. The other outcome is a black hole, and some of you may have seen something like this before. We can think of space-time, so that's the 3 dimensions of space plus time. Think of that as a stretchy sheet. So we're going to convert those 4 dimensions here into 2 dimensions for this analogy. It's a stretchy sheet. If we put something massive on it, it sinks down into the sheet. So think of this as the sun. And anything passing by this massive object is going to start to roll down the hill. So if you push a ball slowly, it's going to roll down the hill. If you push the ball super fast, it's going to start to roll down the hill, but because you pushed it fast enough, it's only going to deflect. This is what happens to light near our sun, or actually near anything massive, but we can notice it with the sun. And this was one of the first tests of Einstein's theory of relativity, comparing the positions of stars when they weren't behind the sun and when they were behind the sun. And this was tested during a total eclipse in the 1920s. But anyway, light will deflect. The more massive the object, the greater the sheet is stretched. So for a black hole, that sheet is stretched down infinitely far. So if we push a ball near the black hole, so if we push it slow, it's going to roll in. If we push it fast, it's going to be deflected. A black hole doesn't magically just suck everything into it. But if something gets close enough to this indentation, it will roll in or fall in and never escape. So that's what's meant by event horizon. Anything that gets a certain distance away from the black hole will fall into the black hole. And typically the size of a black hole is defined by its event horizon, although the actual massive stuff of the black hole is much less of a volume than what's made up by the event horizon itself. Black holes have many different effects. A couple observable effects are the rate of clocks. So a clock that is closer to a black hole is going to tick slower than a clock that's farther away. This happens on the Earth also. A clock that's at the top of a tall tower or the top of a mountain actually ticks more slowly than a clock that's at sea level. Obviously the difference there is super duper tiny, but with really precise clocks, that is indeed noticeable. And if anybody saw the movie Interstellar, they showed this effect. The people that went to the planet, they only aged a few days. The person that remained in the ship aged many, many years because these people's clocks ran slower. That's why Matthew McConaughey and Anne Hathaway look so much younger, because their clocks run slower. It's also why Anne Hathaway, I guess, is so thin. Another thing that happens here is what's called spaghettification. And I hope that's spelled right. For some reason now it looks incorrect. But because the black hole is pretty small and the gravitational pull here drops off as 1 over r squared, the pull on your feet, because so much, the mass is all really close to you, the black hole's mass is all really close to you, the pull on your feet is greater than the pull on your head. So your feet are being pulled towards the event horizon more rapidly than your head, and particles behind you and in front of you are sort of being pulled inward like this. So you're being both stretched out and made skinnier by the black hole. As if you venture out of your spaceship here, you're going to get stretched out like that. Most of that talk there, or all of that talk, was about stellar mass black holes. There are also black holes at the center of galaxies. So our Milky Way galaxy has a black hole at the center that's equivalent to about 4 million solar masses. It's called Sagittarius A star. It's in the constellation Sagittarius. which is a constellation that's very easy to see in the summertime. But the evidence of that, taking pictures, and you can't see with the naked eye the center of our galaxy because there's too much gas in the way, clouds of gas and dust, and that blocks the visible light. But through other wavelengths of light, you can see that. So looking at objects that are in the center of our galaxy, taking pictures year after year, so from 1995 to 2008, these particles moved. And if we plot out the rest of their motion, they all are centered around a certain point. So by looking at the orbital properties of these stars, you can figure out, for one thing, where the supermassive black hole is, and more importantly, you can figure out the actual mass of that black hole. And this picture here is about maybe 1 arc second in the sky, which actually corresponds to just a few light minutes. So things are really, really densely packed at the center of our galaxy.